Okay, so let's attempt this question. So, question states our production line manufactures 100 ohm resistors that have a 10% tolerance. Let X denote the resistance of a resistor, assuming that X is a normal random. Will remain 1,000 ambivariance, 2.5 thousand. Find the probability that a resistor picked at random will be rejected. So, first things first, X follows a normal distribution. The parameters for a normal distribution are mean and the variance of the distribution. So that's something you have to remember. All right. So secondly, the PDF of a normal distribution. So f of x, PDF, probability density function, is a bell-shaped curve, right? So it will look, always looks some similar to this. All right. So three things: x and all the possible values of whatever random variable they didn't look. So in this case, x will be the resistances of all the resistors, and the y-axis will be the probability. Oh, that's f of x. That's f of x, right? So the second thing is that the bell-shaped curve is centered above the mean mu, all right, and the spread of it is denoted by its variance. All right, so the spread basically means how skinny the graph is, whether nice and flat like this one, or to be high up here. All right, so just determine the spread of the data. All right, so it's centered or it's symmetrical about the mean. Its spread is determined by its variance. All right, so the equation for the PDF for a normal distribution or Gaussian, if you want to call it that, is 1 on the square root of 2 pi sigma squared, or Latin the square root, e to the minus x minus mu squared on 2 sigma squared. Right, so there's the equation for the PDF. Right, and we should know from before the normal distribution is a continuous distribution, so that means you'll have a graph, and to get the probability, you need to have the area under the graph. So always remember, for continuous data, the probability is the area under the graph. So all this area here, we know is the probability, and we have different points here. All right, so the area under the graph will give you the probability. And the same law still applies, the total area under this bell curve, so it's still adding up to 1. All right, so two things to keep in mind. The parameters for the normal are its mean and its variance. The bell-shaped curve is the graph for the normal distribution. It's centered about its mean, and the spread is determined by its variance. And the PDF is this equation here. All right, so obviously the probability is the area under the graph. So when we're doing questions, right, you'll have to do the CDF, which is the cumulative density function, right? So this here number is just the probability that x is less than or equal to some arbitrary value x. So how that will look on the graph, I change the color. So for example, so you can see it. If I wanted to know the probability x is less than or equal to some arbitrary value mu plus h, so mu here, so mu plus h could be anywhere here. Yeah. So less than or equal to would just be all this area. All right, so you can kind of see as the probability that x is less than or equal to plus h. All right, same idea if you wanted to do another one. Probability x is more than mu plus h. In this case here, if you're looking at the graph, You have two ways you could do this. Remember, the total area still adds up to 1. So if I was to carve out the green, basically this is what I want here in orange. So it would just be 1 minus the probability x less than or equal to plus each. All right, so just carving out the areas that you need is a good skill to have. All right, so now got out of the way, let's try the question. So the question says that x follows a normal distribution and its mean is 1,000 and the variance is 2,500. They said that you have resistors, 1,000 resistors that have a tolerance of 10%. So all those already built through. So we know it's centered about the and the spread is 2,500. Right? So just a sketch. So since we didn't know tolerance or how tolerances would when you measure the resistors, if it's above or below a certain value, it will be rejected. And that is determined by the tolerance of the resistor. So in this case, it said that the tolerance of the resistors 10%. So that means 10% higher or lower than 1,000. Anything less than or more than that will be rejected. So that means 10% of 1,000 is 100. So that means the lowest it could go is 900. So x had to be less than 900. So if you call this the rejection region, so x have to be less than or equal to 900 and more than, so it'll be 100 higher than 1,000. That'll be more than, so that'll be the rejection region for these. So any resistors higher than this or lower than this, it will be rejected. So like 800 and stuff, we won't take it. So on the bell shape, it will look something like this. So on this side here, you'll have 900, and this side you'll have this. So the rejection region, if you were to shade it, it will be anything here or anything here, right? And this here is the accept, right? So you accept anything in between this range here and reject anything in the two ranges on the outside, right? So we need to get the probability of these two pieces here. So now we'll get into our concept known as the error function and the complementary error function, right? So we'll start with the error function. So the error function, or just f of x for short, right? That the equation for it is 2 on the square root of pi by the integral of 0 to x of e to the minus z or t or whatever squared dz. What that means, let's memorize the bell curve first. Once you memorize how the bell curve will look for it, you'll know which one to use. So we know centered about, we mean spread, same as squared. So for f, that's the error function, right? Because it's symmetrical, so if this is x, this will also be minus x because it's symmetrical about the mean, right? So if we were to use this as 0, set on mu, for if any probability, once you know how to use if, it will be in between here. So that is where the integral came from, because you want probability. So it will be 0 to x, which will be this piece here. And because it's symmetrical, you also have to do this piece. But the good thing about it, because it's symmetrical, once you have this area here, you can just multiply it by 2. So that is where this 2 came from. All right. So if you ever doing a question, for example, and you just specifically just need this piece, sorry, not that piece, the other way. And the center, it's 0, x. All right. So if you need this piece alone, not any symmetrical piece, it will just be half of, which will just be without the 2, because the 2 there to just in case you need both sides. Right? So 0 to x and 0 to minus x. Right? Or on both sides any mean, like how we doing it with the resistors. You will use earth for that. So earth will really bound it from 0 to x. Right? Let's remember that. All right, so the 0 could be the mean. Yeah, so don't get flustered if you're not seeing a 0. It could be the mean. Remember, this here really centered about the mean. All right, but for equation purposes, you just use 0. All right, so we need this, so it'll be half of it. All right, and the second one is complementary error function. All right, so on the bell shape, it will look like him. So it's still centered about the mean, so we just use 0 for now. And the region that you will use this for, so it's still going to x. But in this case, the region is the species, no longer the inside. So the equation for this, we call it C for short, of x. It's still the same equation in terms of how it starts. So in this case, you're going to infinity and minus infinity. So it will be from d0, which is in this case x. You call it x for explanation purposes, because I wrote x in the graph already. So it'll be x to infinity. So notice the integral limits change of e to the minus z squared dz. All right, it's the same equation in terms of these parts here, but the integral different. So the earth goes from 0 or a mean to a x value, so it'll be in between here. And earth is just going from x to infinity, right, which is now what we want. And with that, if you can look at it clearly, earth will be here inside. So if you wanted to get a nice equation to link everything together, earth C will just be the total area, which is 1, total probability, minus earth of x. So if you're to minus earth from 1, you'll get earth C, because the total area is 1. And we know earth is this piece inside it, majority. This is earth. So you notice if you just subtract that from 1, you get earth C. Right? So those are the two, the equation. Here, make sure you know the equation, and also you're seeing this also has a 2 because it could be for 2 sides if needed. If you need 1, it will obviously just be a half of root C, right? Which should just be 1 on the square root of I instead of 2. Because it's symmetrical. Sometimes you'll need 2. So with respect to what we try to do, we want the rejection region, right? So these 2 brown pieces here. So in that case, we want to use earth. We'll use earth C. Right? So earth C is what we want for this question. Right? So setting it up. So the 2 rejection regions will be, remember we limit probability. So the first one is the probability x being less than 900, and the probability x being more than or to 1,100. So these are your 2 rejection regions that will be the limits, right? So converting it into a form that we could use. Remember, we're using the verb C, right? As the derivation that we building up towards, right? So we know that the verb C is already in the form because we're using the two pieces, right? Remember from our graph, if you look at it, it literally looking the same as the verb C. All right, so we could set it up like a normal verb C question. All right, so to do the derivation for this, which is what Bill wanted to do. So the first thing you start with is the PDF. So that's be in this case, will be, well, normal equation, but 2 pi sigma squared e to the minus x minus mu squared on 2 sigma squared. So this is the PDF. And what we want is CDF. Remember, CDF as well as give you equations and stuff. Right, so the first piece. So then for simplicity purposes, we could just work with this range here and multiply it by 2. But that's already going from d0 to infinity, right? So that's like our u is from x to infinity, right? Easier just to work with that piece there because it is symmetric. Nobody likes to work with negatives, right? So in this case, capital F of x would be the integral from 1100 to infinity, right? So 1 and the square root of 2 pi sigma squared e to the minus x minus mu squared on 2 sigma squared. Right, so obviously d dx at the end, right, to the integrated. So you could write this in a better way by moving the integral sign in between. So you could pull out the constants in a way. So you could write it here instead. All right, so we have this here. So from this point, when we set it up, we have to do the derivation of it to get it into OC, right? We know we're working towards. So let's do this. So the first thing we need to do is that we need to make our substitution, right? Because we need to get rid of this complex part here, right? Remember, we're trying to get it into the OC form, right? So if we compare the OC form, it doesn't have all this going on here. So you need to make that change. All we need to do that is let t squared equal to x minus mu squared on 2 sigma squared. All right, so you can make a nice big substitution here. So you end up with 1 on the square root of 2 pi sigma squared integral, and you end up with minus t squared dx. So that's the first piece. So now you're noticing that we have t here, but we have a dx here. So we need to get it in terms of dt, right? So all we need to do is this equation here. This is where we'll get everything we need, right? So what we do is we make t the subject by the formula. So you'll get t being x minus v, because when you square root these two, the square sign will go, and you get square root of 2 sigma, because square root of this will be sigma, the root 2 will stay there. So it does differentiate both sides. So you'll get dt is equal to dx on the square root of 2 sigma, right? Use a constant, right? So the derivative of a constant is 0. So you'll just end up with dx on the square root of 2 mu, right? And we make dx the subject of the formula because that's what we want to get rid of. So dx, that's equal to square root of 2 sigma, make sure and keep it outside, dt. So now we could finally make the second change to make it in terms of dt instead of dx. All right, so the equation will now become, it's 1 square root of 2 pi sigma squared integral from this to infinity e minus t squared square root of 2 sigma dt. All right, so we have this form here now. So what we have noticed is that these things could cancel. So you can write this in a different way. So square root of 2, then you have square root of pi, and the square root of this will be sigma minus e t squared square root of 2 sigma dt. So we can see that this will cancel with this, and this will cancel with this. So you'll end up with 1 square root of pi from this to infinity of e to the minus t squared dt. All right. So right now this is of a form of oopsie, but it's just half of oopsie. So right now this is half oopsie of x. Right, but we don't want a half of oopsie. Remember, a half of oopsie will only give you one of the rejection region or half of the rejection region. So all we need to do is multiply by 2. So let's end up with oopsie of x. When you multiply by 2, get 2 square root of pi. So yeah, this e to the minus t squared dt. All right, and this will be it. Okay, that is the end of that question. All right, so that would be the answer for that. And yeah, so the proof, same steps, make sure you know the proof and the types of errors. So the complementary, make sure you know the area that you'll be dealing with, the equation fit, and yeah, it should be good then. So take it easy and speak.